Hello and welcome back to Unit 5. In this part, we're going to introduce a model for friction. Okay. As we've learned previously, friction resists motion. It always points in the direction opposite of the velocity or the direction the velocity would be in if the object were on a frictionless surface. To help understand the model for friction we're going to develop, we're going to begin by looking at this simulation. I will put this link the link to this simulation on Brightspace for you. When you click it, you arrive at this simulation, and here we're going to look at friction. So what do we have? We have a person, we have a box, and we're told how much friction we have using this up here. What we see is that if we apply a small force to the block or box doesn't move. Okay, and we can keep applying that force, and it gets bigger and bigger. Hold on, until the block does start moving. So now we have to apply it in the other direction. Okay. It gets bigger and bigger, and then all of a sudden, the block starts moving. If we keep pushing after the block starts moving, the applied force increases, but the friction force remains the same. Oh, there we go. Okay, so what is going on here? What you're seeing is the effects of two types of friction. When I initially push on the box, whatever, you're dealing with static friction. Static friction is when something is not moving. Okay. Static friction is a multi-valued force, but it is less than or equal to a maximum value. Once you've exceeded that maximum value, then the object will start moving, and you move into kinetic friction. And as I increase the applied force again, the friction force here stays constant. Kinetic friction is a single valued friction. In both cases, for static and kinetic friction, we have a parameter called the coefficient of friction. For static friction, it is the Greek letter mu sub s, and for kinetic friction, it is the Greek letter mu sub k for kinetic. As I said, static friction is a multi-valued force, but it always is less than or equal to some maximum value. That maximum value is given by the coefficient of static friction multiplied by the corresponding normal force. For kinetic friction, single valued, so kinetic friction equals the coefficient of kinetic friction times the corresponding normal force. If we think about an object, go back to an example we had a little bit ago where we had two blocks stacked on top of each other, and I look at a person pushing on the lower block in this case, I have multiple normal forces on that lower block. I have a normal force between the surface and the bottom block. I have the block's weight. I have a normal force from the top block pushing downward on the bottom block, and potentially multiple frictional forces, but let's just deal with the one between the surface and the bottom block. That one's going to point to the left, because if it were frictionless, the block would move in the direction that the man is pushing on the block. So given my multiple normal forces, which one corresponds do I use when I find the friction there? And the key here is look at these subscripts. They have to have the same subscripts. Okay. Lastly, to give you an idea of how or what these coefficients of friction are, there is a table. This table is here. It is also in your book. You will most likely need values from this table when completing the homework. Okay. So please look up this table, screen capture this table, something, so you have this table. Static friction values, if you look, are almost universally larger than the corresponding kinetic friction value. This is why, for example, when you go to move a large piece of furniture, you have to push really, really hard to get it moving. And then when it starts moving, it suddenly becomes much easier because the friction drops. Right? Another one that always is of interest to me is the bone lubricated by synovial fluid, where the static friction and the kinetic friction are very, very close together. If they weren't very, very close together, then when you go to move your arm or move a joint, it would hitch and not work as well. Okay. This concludes this part. In the last two parts, we're going to deal with examples where we use this model for friction.